All right, in this module, we're going to go over the lever rule, which is the rule that helps us determine the amounts of phases in two-phase fields um, that we've been talking about. So specifically, we'll look at the isomorphous system. So, as I just said, the lever rule is used to determine the amounts of phases. In the previous modules, we just determined the composition. So again, if you could kind of pinpoint the alpha region in a two-phase field, what the composition would be is how many nickel and copper atoms would be in that phase, or the same thing for the liquid. The amount is if we were able to sort of magically separate the two and weigh them out, right? So would there be 50 weight percent of the one phase and 50 weight percent of the other, or what would that be? So it's basically like measuring the amounts of those phases in a mixture. So that's what we want to do with this. So let's look at a similar composition and temperature and in this two-phase field and see if we can determine the amounts. So this is typically going to be weight fractions of those phases. So we're going to again go with the 35 weight percent nickel, which you can see here is the purple line. And we're specifically going to look at that temperature TB because that's within the two-phase field. And we're going to go ahead and draw our tie line. So you saw that, this in the previous modules, we had this tie line drawn at that given temperature. So we have that. However, we have a tie line here with the endpoints being the compositions, right? Cl and C alpha. But we can use the relative amounts on either side of our compositional point. So C naught, right? And you see that this side is labeled as R and this side is labeled as S. And you can clearly see S is bigger than R compared to, if you're comparing those two. So that's what we're going to look at. So again, here you can see if we're talking at the first temperature up here, that we just have one phase. And so our weight fraction of the liquid would be 1 or 100%, and then alpha would be 0. At TD, which is down here in the solid region, then our weight fraction of alpha would be 1, and our weight percent would be 100, and liquid would be 0. But in the middle, what we're going to do is we're going to use the so-called lever rule, and that's, the tie line and the relative amounts of each side of the composition. And so what we do is for the liquid, so the weight fraction of liquid, what we're going to use is we're going to use this region of the line, of the tie line, S. So what we're going to do is we're going to take the length of S divided by the total length R plus S. So R S over R plus S. And then for alpha, we're going to take R, this length, the green line, over the total length R plus S. And so you may be asking yourself, why do we use these particular lines? And that's where the lever rule and the name of it comes into play, is that for the liquid, we saw the composition of the liquid is on this side. And so we take the opposite length of line, which is S. So that's between the alloy composition C naught and the composition of the opposite phase, C alpha, and vice versa for the alpha phase. We take the opposite length, which is R. And so if we want to do that, so let's just run through the numbers real quick. So S is going to be equal to C alpha minus C naught. So that's 43 minus 35, which is what you see up here. And then the combination, the length of the total line is going to be 43 C alpha minus CL, which is 32. And so that's the 43 minus 32. And that would give you a weight fraction of 0.73 or 73 weight percent liquid. And then the rest of it has to be alpha. So you can just take 1 minus 73 0.73, or you can go through and calculate the distance of r, which would be 35 minus 32 over the total length, which stays the same. So that's the lever rule. And let me bounce over to the piece of paper, and I'll just kind of go through this in a little bit more detail so that you can see why we call it the lever rule. All right, so let's look a little bit more in detail at this lever rule, or lever rule if you want to call it that. So I've tried to redraw the figure here. So we're looking at 35 weight percent, which is this dash line, vertical dash line, and we're looking at 1250, which is approximately this dash line. So we're at a point here. We know that this is our alpha plus liquid region. This is liquid up here. This is alpha down here. So we know at this temperature, we can draw a tie line, and the endpoints here, this is CL, and this is C alpha. So our compositions of liquid and alpha respectively. Our alloy is 35. And from this this tie line, we can think of this as our this is our lever. So let me draw this just independently. So let's say I have this tie line, right? So this is C liquid, this is C alpha, and our fulcrum for the lever, right? That's our alloy composition. And so you can think of each of these as a lever, or sometimes teeter-totter on the the playground, right? So if you put a mass of liquid ml on this side, it causes the other side to raise up. And then if you put a mass of the alpha on this side, it would cause this to raise up, right? And these fulcrums, this distance we called r, right? This is the distance here, r, and this is s. That's just how the book denotes them. And then this one is s. So the total length is r plus s. But to get this to balance, right, with this fulcrum here and these masses here, that's why we kind of think of it as a lever, right? The mass balances here. These masses have to balance with where the placement of the fulcrum is. And so that means that this has to be a larger mass than this one, and therefore it's the opposite side. So it uses S. And so I always like to think of it as the opposites. So if you're looking for the weight fraction of the liquid, which is on this side, I'm going to use the opposite length. So from here to here. So I'm going to use S. And then it's always divided by the total length, so R plus S. And then if I have the alpha's over here, and I'm going to use the opposite length because that is what has to balance the mass of alpha. So we have R plus S. And when you have these numbers, so again, we're calling these R and S, but what we really mean is that S is the length here. And so that is, this quantity was, I believe, 43. Yes, this is 43. So I might not have it drawn great, but this is 43. This is 32 from the previous question. And so the quantity the quantity S for this quantity here is going to be C alpha minus C naught. And then the total length is going to be from here to here. So C alpha minus this total length over here. So CL. And then it's going to be for R is going to be from this point to this point. So C naught minus C liquid over the same length. So C alpha minus CL. And so we can put numbers to all of these quantities like we did in the previous page, because this is 43, this is 35, and this is 32. So when we plug that in, we get what we saw in the previous. But I just kind of want to go over this drawing, right? Because this is basically why we call it the lever rule, or you can think of it as a teeter-totter on the playground. And so these have to balance. And so the way we do that is by looking at opposites. So liquid S, alpha R, or whatever the two phases are, you're always going to look at the opposite. So these two are connected and these two are connected for the numerator.